If you finished the last video scratching your head a little bit about, well, wait a second here, we've got all these active connections upstream. How exactly are we preventing broadcast storms in that scenario? Well, you're in luck because we are going to dive deeper into the networking of those fabric interconnects and really understand how exactly we deploy VLANs into that space and how we handle these broadcasts. Let's jump in and get this resolved. So let's say we have our pair of fabric interconnects and we're connecting that up to the rest of the network. And as we recall, we could have a lot of different connections. We're connecting up to probably our access layer switches. And so maybe we've got, let's just say 4 connections on this side and 4 connections on this side. And again, from a logical perspective, each one of those could be a port channel up to the LAN. Now the idea here is this. Typically speaking, we're going to apply VLANs to our fabric interconnects. And for the most part, we should have the same VLANs on both sides. For example, if I want to configure VLAN 10, then that should be VLAN 10 on the left and VLAN 10 on the right. If I want to configure 20, then 20 should go on both sides as well. However, in some cases, we might not need that. There might be a special situation where we have a part of a network hanging off of one of the fabric interconnects and not the other. But for the most part, we're going to see that the VLANs are the same between the two fabric interconnects. Now, what might not be the same are the VLANs that are allowed on all of the upstream connections. For example, I might allow VLAN 10 on the link on the left, and I only allow VLAN 20 on the link on the right. From the fabric interconnects perspective, this is known as a disjoint layer 2 domain. And we call it that because we don't have the exact same VLANs on all of our uplinks. Now, disjoint layer 2 used to be a bigger deal in the UCS space. We had to configure around it and such. But nowadays, this is almost expected behavior. We'd expect possibly to send our data traffic out one link and our DMZ traffic out a completely separate link like we talked about. Now, all that said, a VLAN is essentially a broadcast domain. And so if we're splitting out our VLANs, or maybe we have the same VLAN on all of these interfaces, maybe VLAN 10, for example, is extended on all 4 of those connections. Well, in this case, we need to start to understand how exactly broadcasts are handled in the fabric interconnect domain. So in order to understand this, let's start with saying that we've just received a frame from a downstream connection. This is a broadcast frame. It arrives on a particular interface, and now the fabric interconnect has to decide what to do with it. Well, there are 2 sides to this. Remember, downstream, we know that we are learning all of the MAC addresses. However, upstream, we're treating this a little bit different, and we're going to use this concept of pinning instead. And so what we need to do is, first of all, we need to send this traffic down all of our downstream connections. Because it's a broadcast, it's supposed to go everywhere. And so as long as a downlink is in the particular VLAN where this broadcast arrived, it's going to be sent down that physical connection. And I say physical connection, but really it's going to be extended down to every single virtual NIC that happens to be in that VLAN. So again, we talked about those virtual Ethernet interfaces. So if a VETH is inside of that particular VLAN, then that VNIC that's attached to the VETH is going to receive the broadcast. And that's exactly what we want. However, from an upstream perspective, we're not going to send out all of these uplinks. Because remember, upstream, we're not operating as a switch. Instead, we're running in end host mode, and again, we're using this concept of pinning. So which of these uplinks am I pinned to? Well, let's just say we're pinned to the first one. So because this is my pinned link, I'm going to send the broadcast up to the local area network. So problem solved, right? Broadcasts are resolved, absolutely nothing else to need to worry about. Except there kind of is. Because we know that the upstream LAN consists of traditional switches. And traditional switches are going to do what switches do, and they're going to receive a broadcast and send it out all of the links in that VLAN. Well, I just said that, let's say VLAN 10 is enabled on all 4 of these connections. Well, that means I'm going to receive that broadcast back on all 3 of those connections. Furthermore, the fabric interconnect on the right is going to receive it on all 4 of the connections. And again, to be clear, we are assuming that VLAN 10 is enabled on all of these links. Now, unfortunately for us, we can't go to these switches and say, hey, you know what, we're special, so don't send us broadcast messages. I mean, we actually do kind of need the broadcast messages, so it gets a little complicated to suggest that we should somehow change how the switches behave. But we don't want to touch how the switches behave. We can expect this to happen regardless of whether the upstream switches are Cisco or not Cisco. And so we need to deal with this situation head on from the fabric interconnect's perspective. The way we deal with this is with the concept of a designated receiver. The designated receiver is going to be a link that is on that VLAN that is going to be used to receive the broadcasts. So let's just pick a couple of these at random. Let's say that this link right here is my designated receiver on the left, and let's say the rightmost link for the fabric interconnect on the right is the designated receiver. So let's look at the fabric interconnect on the right. So we're going to receive this broadcast packet on the designated receiver, and that will get forwarded out to all of the downstream connections. So that's fantastic, good to go. So what about those other 3 frames that are arriving? Well, we know that they're arriving on not designated receiver links. And because of that, we are going to drop those broadcasts. We're assuming that, hey, if I'm getting broadcasts on the non-designated receiver link, then I probably did get one on the designated receiver. And so I got a copy of that broadcast. I have propagated it downstream. I don't need another copy of that frame. Now, the designated receiver is chosen on a per VLAN basis. And yes, we can have one link be the designated receiver for many VLANs. So the link could be a designated receiver for VLAN 10 and VLAN 20 and VLAN 30. And then we could have a different link be the designated receiver for VLANs 15 and 25. And for the most part, this is going to be a function of the fabric interconnect itself. We don't have to manually configure the designated receivers. And so a lot of this configuration is performed for us. And for what it's worth, this is going to happen regardless of whether the broadcast is coming from an upstream or a downstream perspective. So I use the example of it coming from the downstream. It came from a server and it went up and we sent it out the pinned link. But if the broadcast had originated from the network and had been sent out this way, well, we'd be treating it the same way. We would receive that broadcast on the designated receiver side, and we would drop the rest of the broadcasts that we receive on the other connections. Okay, so now we are officially good to go, right? We have blocked all of the bad broadcasts. We are only allowing one downstream. We are good to go. Except maybe not quite yet. If you're really paying attention, you might actually have seen the problem that still exists on this diagram. And that is back over here on the original fabric interconnect. We said that a broadcast packet showed up on that fabric interconnect, got sent out the pinned uplink, and then came back down all of these other connections. But in this scenario, the designated receiver is a different link than the pinned uplink. If it happened to be the pinned uplink, then we'd have no problem because the LAN isn't going to bring it in on one interface and send it right back out the other interface. And because the switches will never do that, then hey, problem solved, we're not getting an extra copy of the broadcast. But this packet right here that's being sent down on the designated receiver, by any other rule, is going to be forwarded down to all of the switches downstream. So this would be considered a duplicate packet. We don't need to send the same broadcast message 2 times to all of the servers in our infrastructure. So what do we do about this? Well, this introduces the concept of a deja vu check. The deja vu check is going to check the source address. Where did this frame come from? And we're not just talking about broadcast, by the way. This applies to all kinds of traffic, unicast traffic, broadcast traffic, multicast traffic. When a frame comes into an upstream interface, we're going to find out, hey, does that source MAC address exist downstream? And if it does, we are going to drop that packet. And the reason we're going to drop it is because only one of 2 scenarios is happening here. Either one, somebody is spoofing a MAC address that exists downstream, and that's no good. We don't want to allow that traffic to enter into the UCS domain. But the other situation is that we've already seen it. And because we've already seen it, this is where the name deja vu check comes from, because the feeling of deja vu is, wait a second, I've seen this before, I've felt this before. And so UCS is saying, wait a second, I've probably already seen this. And the reason I've probably already seen it is because if the MAC address lives downstream, then that packet must have arrived on a downstream interface. And because it must have already arrived on a downstream interface, I probably already processed it and did with it what I was supposed to do. So because of the deja vu check, we can safely drop this frame that comes in because the broadcast message was sourced from a downstream MAC address. Now there is one other rule that we need to learn, and that is the RPF check. And the RPF check comes back to this concept of pinning. We remember that if I am pinned to a particular uplink on a Nexus, let's just say I have an upstream Nexus 9K, and so I know I've got an Ethernet 1/1 link, and I have pinned a particular VNIC to that Ethernet interface. Well, because of that, the upstream switch should learn that MAC address as being out Ethernet 1/1. So if my MAC address is MAC address A, then hey, that Nexus 9K should have in its CAM table MAC address A maps to Ethernet 1/1. And that's well and good, other than what happens if I happen to receive a frame on a different interface that's destined for MAC address A. Well, something is amiss at this point. Something is failing to converge in the upstream network. Something may have gone down and caused problems. I don't know exactly what's happening here, but this tells me that I'm at risk of a loop, because I should only be receiving traffic for a particular VNIC on its pinned interface. If that traffic is coming in any other interface, then I need to drop it. So the RPF check actually checks the destination. When a frame comes in, I check the destination, and if it's the pinned interface, then I'm good. If not, then I drop it. So we have the deja vu check and we have the RPF check. Both of these are kind of advanced technologies that are going to prevent loops and unexpected behaviors in our environment. The difference primarily is that the deja vu check is going to check the source address, and the RPF check is going to check the destination. And so we always want to make sure that the traffic coming in, first of all, wasn't sourced from a device that is downstream, and second of all, is arriving on the appropriate interface. Now, I tell you what, this kind of conversation really gets me excited because this is networking. This is routing and switching. A lot of us have Cisco backgrounds. And so as we jump into the data center space, we might be saying, oh, I don't know if I'm comfortable with servers. Remember, UCS was This is this beautiful solution that's designed to integrate networking all the way down to the server. And so the more we dive into this, the more we're going to see how exactly Cisco designed these network flows to occur. So first of all, we start with the VLANs. The VLANs are created on each fabric interconnect. Technically, they can be created individually, but for the most part in UCS Manager, we're just going to push those same VLANs down to both sides. Now, they should be allowed also, by the way, on some number of uplinks, and if they're not, I suppose, then there's almost no reason to have them. All right, so second of all, the designated receiver is going to be mapped to a particular link for each VLAN. Remember, it's a per VLAN configuration, and so we're going to have a link that gets automatically chosen as the designated receiver, and that is the only interface on which we're allowed to receive broadcasts. Broadcasts coming into any other interface for that VLAN will be dropped. And lastly, we talked about those other two checks. The deja vu check and the RPF check, those are both going to make sure that we've got a stable environment, that we're not looping traffic and we're not receiving traffic on bad interfaces and such. The deja vu check is going to check the source interface, and the RPF check will check the destination interface and make sure it's arriving on the pinned link. I hope this has been informative for you. I'd like to thank you for viewing.